And we're live. Okay. Still have a few more readings up here, both for Thursday and for today. If you haven't gotten one, you can pick them up after class. It's really important to do the reading because, we're going to go in the lectures at a more advanced level than what is being dealt with in these chapters. So you definitely need to be up to the level of the reading before you can really jump in on the lectures. So today we're going to be talking about linear models using Stan. Again, not having to write stuff in the Stan language. Martin. Yourself, but using an R package that already comes with a bunch of Stan models, and so all you have to do is specify the R syntax, which ought to be pretty familiar to a lot of you, and then you'll be able to get draws from the posterior distribution. I'm Ben. I'm biased. I don't even have time to deal with this today. We got too much to go through. Okay, so. Linear model. Here's sort of two ways of expressing a posterior distribution. You can sort of do it in terms of words, or words that sort of specify distributions, or you can do it in terms of the terms of a PDF. So we're going to do it both ways. So to start off with, we're going to make an assumption about the error term in the way the data are generated according to a linear model. So the error term is the difference between the outcome and the vector product of our predictors and our coefficients beta. If we assume that's distributed IID normal with mean 0 and standard deviation sigma for all observations, the shifting property of the normal distribution that we've discussed many times before implies that each observation y before we observe it has a normal distribution. The means differ from one observation to the next because in general the x's can differ from one observation to the next, but the error terms all have a common standard deviation sigma. So this is our assumption about the data before we see it. Once we have data on y, then this in effect becomes the likelihood function that we want to condition on when we do stuff. Somebody pass this back to Adam. So there's in the Bayesian literature, there's sort of different ways of parameterizing a linear model. If you were going to do a Gibbs sampler, which we're not, but if you were, it's a little bit easier if you parameterize the model in terms of the precision. The precision is defined as the reciprocal of the variance. So I'm going to call that precision tau, and sigma is equal to the square root of the reciprocal of tau. So it's really just a notation thing. It makes sense if you were to do Gibbs sampling, but we're not. So that's just a deterministic equation. There's no additional randomness in the expression sigma equals the square root of 1 over tau. But if tau is going to be the parameter, one of the parameters that we're going to get the posterior distribution of, we need to have a prior on it. And for now, I'm going to assume tau has a Jeffreys prior, which is to say its density is proportional to 1 over tau. However, that's not actually a proper density function because it doesn't integrate to 1. It integrates to infinity over the positive real numbers. So this is a improper prior, but nevertheless, if you have more than 2 observations, it's going to yield a proper posterior distribution, so people don't get too worked up about that. Finally, I'm also going to have an improper prior on betas. I'm merely going to say they're any real number in k dimensions. K is the number of x's that I have. This is also part of an improper prior on the coefficients, basically saying every small region in the real numbers in k dimensions is equally probable. So does anybody have any questions about sort of the verbal description of the posterior distribution I've just described? Yes?
What's the difference between beta being like RK versus beta being distributed like uniformly across?
Yeah, I used to say uniformly, but to say it's uniform sort of implies that it's proper, and it's not. So we're just going to say beta is any real number, set of real numbers here in k dimensions.
Y is normal, yi.
Yes.
Normally distributed. Sigma, can't we make an assumption of that being also sort of sigma is the sum of residual sums squared?
No. Sigma is just an unknown parameter. In ordinary least squares, you can estimate it with like the average of the square residuals. But when the Bayesian approach, it's just an unknown parameter that we're going to estimate. And we're going to estimate it as the square root of 1 over tau. So I can write the equivalent information in terms of PDFs or improper PDFs. So I want the posterior distribution of beta and tau conditional on y and x. That's proportional to my prior on beta, multiplied by my prior on tau, multiplied by my likelihood for each observation, multiplied over all the observations. So my prior for beta is just a constant. The Jeffreys prior for tau is 1 over tau. And then I multiply by the blue thing here, which is the normal likelihood for the data, well, not for the data, of beta and tau, but evaluated at the data that we have. We can simplify that a little bit to collect terms that are similar, pull some of the taus out, things like that. So these two things have equivalent information. They describe the same posterior distribution. One is a little bit more with like words, and the other I actually substitute in the PDFs, where the words were. So if I say normal, for y, then I'm going to have this normal distribution here when I evaluate the likelihood. It's two sides of the same coin. Okay. It's often a little bit easier to describe yourself if you use this sort of top characterization of the posterior distribution. But when you get right down to doing it in stand code or really anything, you're going to have to actually write down the math of the PDFs. Now, there's no reason why you would have to do like, all this. You can just do dnorm in R, or there's an equivalent thing in stand to say like, I want the normal PDF. So you don't actually have to write out all this unless you're using a distribution that isn't already programmed into the language you're working with. Questions about that? No? Okay. So this, with these priors and this likelihood, it's actually one of the extraordinarily rare cases where there's something close to a closed form solution. So if we write the posterior distribution of beta and tau as a marginal posterior distribution for tau multiplied by a distribution for beta given tau, so the multiplication rule implies this is the same thing on the left, which is the posterior distribution we're looking for. And this stuff in red and blue is just copied from the previous slide. It's our posterior kernel. So I'm going to say, okay, if this is our posterior, how do we draw from it? To make things slightly simpler, I'm not actually going to prove this, but just to make it simpler, let's define B as the ordinary least squares estimates, x transpose x quantity inverse times x transpose y. That's the OLS coefficients. And E is a vector of residuals defined as my y vector minus x times b. So I have those two quantities before I even start. So what I'm not going to prove, but is true, that if we want to get the posterior distribution of tau given y and x, we can take this expression here and integrate beta out of it, leaving a function of tau alone. And that function is going to be proportional to a gamma PDF that has shape n minus k over 2 and rate sum of squared residuals over 2. So that gives us the marginal posterior PDF for tau. Similarly, you can sort of see here, if you take tau to be a constant, you can just drop it and you're left with this, which is the kernel of a multivariate normal. The PDF for beta conditional on tau is going to be proportional to a multivariate normal PDF whose mean vector is B, the OLS solution, and the variance covariance matrix can be written as sigma squared times the quantity X transpose X quantity inverse. So that might look very familiar as, you know, at least in expectation, it's the same as the OLS regression coefficients, and the variance covariance matrix is the same as the OLS variance covariance matrix of the estimator if you plug in an estimate for sigma squared, which is typically going to be the sum of squared residuals divided by n minus k. We're not going to do that in a Bayesian context. We're just going to draw from these distributions. But another thing that could be said is if you go back to the red and blue kernel here and you integrate tau out of that to obtain a marginal posterior distribution for beta, that works out to multivariate student t, which is the same distribution as the sampling distribution for the OLS estimator. So what's going on here? Basically, for these priors and this likelihood, we have an eclipse of the frequentist solution and the Bayesian posterior distribution. So they're the same distribution. They only have philosophical interpretations. So in other words, you know, if you have this likelihood and these priors and you condition on the data that you have, what you believe about beta, for example, has to be multivariate student t with expectation b, the OLS regression coefficients. So that's sort of your interpretation or your beliefs about beta conditional on the data if you have these particular priors. If your cousin is a frequentist and that person repeatedly draws in observations from the population, does this over and over and over again, the distribution of the OLS estimator for the coefficients will also be multivariate student t with expectation equal to b, or expectation equal to beta, the true regression coefficients in the population. So in this case, both the Bayesian posterior distribution of beliefs and the distribution of the OLS frequentist estimator are the same distribution. They're, you know, they have differences in interpretation, but honestly, if you did OLS and interpreted it as characterizing this posterior distribution, it wouldn't be the worst thing in the world because they are the same distribution. However, if you're going to do that, which you should not, but if you were, you're just going to like do LM on your computer and get OLS regression coefficients and then interpret the confidence intervals and stuff like that as if they were Bayesian posterior intervals. In order to do that, justifiably, you would have to believe these particular priors, because these particular priors are what cause the Bayesian posterior distribution and the frequentist sampling distribution to be the same multivariate t distribution. And so you would have to believe a Jeffreys prior for the precision is a good prior to have. And it's really not. So if tau is the precision, the reciprocal of the variance, under the Jeffreys prior, your modal belief about the precision is that it's 0. So the variance is infinite. And that is a pretty ridiculous thing to believe. If you actually believe that, why would you go out and bother collecting data? You're not going to, learn anything from it. So these sorts of prior beliefs don't really make a lot of sense. but they're the prior beliefs that you would need to have in order to do a frequentist thing and interpret it as a Bayesian posterior distribution. Okay? So supposing you want to do that, you don't actually need a Markov chain, or you don't need Stan or anything like that. You just need Monte Carlo simulations, calculate the OLS regression coefficients, calculate the residuals from that, and then repeat the following 4 steps an approximately infinite number of times. So you draw tau, which is the reciprocal of sigma squared, from a gamma distribution with shape n minus k over 2 and rate summa squared residuals over 2. Use that draw of tau, take the reciprocal of it. Now you have a draw of sigma squared. Draw beta conditional on sigma squared from a multivariate normal distribution whose mean vector is b, the OLS regression coefficients, and whose variance covariance matrix is equal to the draw that you just obtained of sigma squared multiplied by x transpose x quantity inverse. Now there's a more efficient way of doing that, which we've learned, which would be to just draw a vector, let's say k values z, independently and identically distributed from a standard normal distribution, multiply z by L, which is the Cholesky factor of x transpose x quantity inverse, multiply that by sigma, add it to b, and you have a draw from the multivariate normal distribution in step 2. But that's really just an efficiency thing. Any way of drawing from a multivariate normal distribution is going to be fine here. So that's step 1, that's step 2. If you want to draw y from its posterior predictive distribution, then you can just draw that from a univariate normal distribution using your draw of beta as the coefficient vector and your draw of sigma as the standard deviation. This is what you believe a future y would be for a given x, and it has a normal distribution as well. Step 4 is optional, but if you're interested in some function of the outcome, which you often are, you can evaluate that function, which I've just arbitrarily called g. And then you go back to step 1 and do the whole thing over and over again, maybe thousands of times. This is actually pretty efficient, so you could do it a million times and it wouldn't take very long. In the end, you're going to get draws from the posterior distribution of tau, sigma, beta, and y tilde, and whatever g of y tilde you might be interested in. So in this case, we can actually get independent draws from the posterior distribution by following these 4 steps. But almost no other case are we going to be able to do that. And in this case, it only worked because I chose very particular priors that made it work. Not that I had any argument as to why those would be good priors. In fact, I have arguments as to why they're not. But before Markov chain Monte Carlo was invented, you actually could do a Bayesian analysis with a linear regression model, as long as you had the ability to draw from a gamma distribution and a normal distribution. All right? Questions about how you might go about doing that? If so, here's a little bit of our code that corresponds to the same thing. I didn't draw y from its posterior predictive distribution or have any g of y, but this will produce draws from the posterior distribution of beta and sigma. And if you really cared about the tau, you could just do 1 over sigma squared and you have distribution of tau. So you can try this on your own. Here, I'm going to do it on a data set called political economy risk. So the outcome variable here is called BRB2. It has something to do with the black market exchange rate. So the higher the sort of black market exchange rate is to the official exchange rate in a country, that suggests more political economy risk for like investors and people like that. I'm going to use as predictors all the variables in that data set except the country name. So this is cross-sectional data. If we had data over time, then I might actually condition on country dummy variables. But in this case, it's just cross-sectional. I call the function called draw, which was defined on the previous slide, give it y and x, and say I want 1,000 simulations from this posterior distribution. I get them back. I can estimate using Monte Carlo integration what the true posterior means are just by taking the column-wise means of these 1,000 draws for each dimension of the posterior distribution. And what we get back are these posterior means in our model predicting the black market exchange rate premium. Question, Nigel?
These values,
Or
these outputs like PRSC 21 and 22, what are these?
So CRTS has something to do with the courts. Honestly, I forget what the PRSs stand for, but it's described in the MCMC package. Yeah, it's something about country. So GDP2, I think I know what that is. It's like log of per capita income. Don't get too hung up on what the predictors are. It's just trying to show the process here. Nigel?
Do we use the means or the mode?
The mode is evil, and these are the means. But also, it's a little bit, from just draws, it's kind of hard to figure out what the mode is because every point is going to be unique. So the mode of like a continuous distribution, it's a little, if you don't have an analytical form, it's, you know, but it's not worth calculating anyway. Okay, question? Yeah, anybody? All right, rolling along. So how might we generalize this to some other priors that are not the priors that are cooked up, quite frankly, to make the Bayesian posterior distribution coincide with the sampling distribution of the OLS estimator in the frequentist perspective? So right at the outset, you shouldn't, and I know it's tempting to do, should not think about priors as sort of a vulnerability or something that someone else could criticize you. I mean, they will do that, but that doesn't mean that you should think in those terms. You should be thinking of priors as an opportunity to get more precise posterior distribution by contributing information about this data generating process that you know to be true. So to a limited extent, if you choose particular priors, we can actually do informative priors and still get a posterior distribution that we can deal with in closed form. So that entails putting an inverse gamma prior on the error variance with some shape and some rate, and a multivariate normal prior on the coefficients with some mean vector and some covariance matrix sigma squared times B naught inverse. So how would we interpret these things? You can interpret B0 as a hypothetical or even a real previous estimate of beta. So if you did like a pilot study or something like that, and you got some regression coefficients, you could use that for B, lowercase b0. Or you could just pretend that you did a previous study and put in your best guess for B0. Similarly, capital B0 is your previous estimate if you have a previous estimate of X transpose X. Otherwise, you can just put in your best guess for that. But as capital B0 approaches a zero matrix, this prior becomes less and less informative. And there's a special case where the little b is a zero vector and the big B is something proportional to an identity matrix. And this is going to be the Bayesian version of something you might have heard of before if you took data mining, called ridge regression. But you could use other values of little b and big B if you want. What are C and D? So C is a previous estimate of n minus k. If you actually did this study before, then you know exactly what n minus k is. If not, you could use kind of a lower value. Again, putting that in is something close to 0 is going to be less informative. And D is a previous estimate of C0 times sigma squared, otherwise known as the sum of squared errors, which if you have a previous study, you would easily be able to plug that in. If not, you can just make something up. Again, given the OLS regression coefficients, which you can pre-calculate, the posterior distribution is going to factor into a marginal posterior distribution for sigma squared and a conditional posterior distribution for beta. Given sigma squared, you can draw from this distribution of sigma, draw from this distribution of beta, draw from the posterior predictive distribution of y, evaluate any g of y function you want, go back to the beginning, draw sigma squared from its posterior distribution again. With informative priors, these are more tedious to evaluate, but it's really just math. So the posterior distribution marginally for sigma squared is going to be an inverse gamma with this shape and this rate. And the conditional posterior distribution for beta given sigma squared is going to be a multivariate normal with this thing multiplied by that thing as the mean vector, and variance covariance matrix equal to sigma squared times the inverse of this. So with Stan, you wouldn't have to choose these particular informative priors. You could use any informative priors that you want. But prior to Stan, there was a lot of people, when they wanted to do regression, but do it the Bayesian way, sort of forcing their beliefs in terms of an inverse gamma on sigma squared and a multivariate normal on beta, because we have an algorithm to draw from this posterior distribution that doesn't actually require a Markov chain and thus entail the dependence between the draws. This was, you know, derived and whatnot when Markov chain Monte Carlo, before it even existed, but it was still used a lot even when Markov chain Monte Carlo existed, but just wasn't particularly reliable in its, you know, first implementations and whatnot back in the 1990s. So you don't have to use those particular priors that I started with. If you do, that makes the posterior distribution and the sampling distribution of the OLS estimator be the same multivariate T distribution. You can still get draws in closed form or draws that are independent of each other if you have informative priors, provided you can describe your informative prior beliefs in terms of an inverse gamma prior on sigma squared and a multivariate normal prior on beta. If you have some other kind of beliefs, then this on this slide won't work, although you could probably do it in Stan relatively easily these days.
So when you say multinomial on beta, you mean multinomial on what beta is distributed at, which is a normal. So norm
yeah
is assumed distributed as normal.
Multivariate normal.
And it has the mu and a sigma, and then those mu and sigma have these. Right?
Yeah, so this is multivariate normal for beta. Multivariate normal distribution has a mean vector and a covariance matrix. So it's not the case, unless B0 is diagonal, that your prior can be described as a product of univariate normals. In general, you could have beliefs about the covariance of the K coefficients. But a lot of times, so with like ridge regression, the B is diagonal, in which case it does reduce to the product of univariate normals.
Don't we want to do the whole thing where we have hyperparameters?
No. I mean, yeah, you probably do, but if we're talking like in the 1970s, you don't, because that would mess up this. Like this was the only way to get draws from the posterior distribution before there was MCMC. So you couldn't start getting creative with any of this, or your creativity is limited to what you can express inverse gamma prior on sigma squared, multivariate normal on the coefficients. But that's the only thing you're allowed to do if you want a feasible algorithm to draw from this posterior distribution. That was then. Today, that's no longer the case, but
right, I mean, these are not hyperparameters.
these are not hyperparameters. We're not estimating B0. We're specifying a value of it. Ideally, specifying it to be, you know, whatever it was the last time we did this study, because then it would be less controversial. Okay? So, but even before there was MCMC, there was ability to do Bayesian linear regression model. Limited, but possible. So what if we want to change the priors? So we're going to describe a new posterior distribution here, one that entails Laplace, otherwise known as double-exponential priors. We're going to start out the same way by assuming the error term is normally distributed with mean 0 and standard deviation sigma. That implies y has a normal distribution with mean x transpose times beta. We're going to use a Laplace prior for each of the coefficients. However, for the intercept, which I'll call beta 1, we're just going to have an improper prior there. It can be any real number. And to complete this posterior distribution, even though it sounds ridiculous, I'm going to take sigma, which is the error standard deviation, and s, which is the scale parameter in the Laplace distribution, to be fixed. Now, you haven't seen the Laplace distribution yet, but I'll have a picture of it, of its PDF coming up. If you do this in terms of PDFs, for beta, conditional on all that stuff, you have kind of the same likelihood that we had before in blue here. And then the logarithm of the prior, the Laplace prior on the coefficients, can be written as the absolute value of beta divided by s, where s is the scale parameter of the Laplace distribution. You can pull out that 1 over s out of the sum, and the sum comes from doing the logarithm of the product from k equal to up to big K, and also the logarithm of the likelihood that we have for the normal distribution here. So you've not heard of the Laplace distribution yet, I don't think, but we have sort of here a perfectly valid description of a posterior distribution if our beliefs about the coefficients beta can be described with this Laplace PDF. But now we've gotten creative a little bit, not that creative. And now there's no closed form algorithm to draw from the posterior distribution. We would have to do, we could do some Gibbs stuff, but ultimately we have to do MCMC to draw from this posterior distribution, because the posterior distribution doesn't break up into like a marginal distribution of this and a conditional distribution of that, where we know what the distributions are and we already have algorithms to draw from. So as far as you're concerned on this slide, all we've done is change the prior on the betas from normal to this thing called Laplace. And now we would have to use something like Stan to draw from this posterior distribution efficiently. Yes?
What's the Laplace sign on the first line be?
Assuming the errors are normal with mean 0 implies that y is normal with mean x transpose beta.
It's only if that moves them.
Yes. Yeah, yeah. It's actually, it's if and only if, but we won't worry about the only if part of it.
And why are we not like in the literature, sometimes we assume the errors are also like, you know, differently distributed than normal, and then we have link function going on.
No link function.
So
We'll do that Thursday.
but like, is it, what do we more focus on? Do we focus more on the distribution of betas, or do we ignore that, say that EIs are always normal?
Both parts go into the posterior distribution. You know, one's your likelihood, one's your priors. So yeah, you have to sort of make your choices about both of them. These are simplistic choices, definitely. All right. So if you look at this kernel of a posterior distribution in log units, and you remember back for those of you who took data mining with me the first semester, that log kernel is equal to -1/2 times the function being minimized by the so-called lasso estimator. So the assumptions about the data generating process with this posterior distribution are the same as the assumptions that the lasso procedure is estimating. However, lasso traditionally is a optimization approach, which is to say they're going to find the mode of this posterior distribution. And as I said a few minutes ago, a posterior mode isn't even worth calculating. It's something that's optimal under the highly suboptimal loss function, that your loss is 0 if you get the parameters exactly correct, and your loss is some constant if you get the parameters even the slightest bit wrong. If you take the expectation of that loss function, then the optimal estimator is the posterior mode. But that loss function is completely inappropriate for science, business, policy, anything else that I can think of, because it doesn't distinguish between, a close miss and a large miss. You're gonna miss. But for all kinds of things, you would rather miss a little bit than miss a lot. And this sort of knife-edged loss function does not reflect that. But the posterior mode may entail that the mode is at 0 for some of these coefficients, which is the feature of lasso that makes it incredibly popular among data mining people. That you can do this and you come back with estimates for some of the betas that are exactly 0. In which case you sort of conclude that you didn't need to put that predictor into the model. So lasso has this sort of automatic variable selection thing to it. But if you sort of take the Bayesian perspective on this, all you've done when you say, okay, the posterior mode is 0 for some beta, is ignore all of your posterior uncertainty. And so the part of lasso that lasso engineers are attracted to is the intellectually dishonest part of it, where you just ignore all your uncertainty and proceed as you were. Bayesians are usually going to be seeking the posterior mean or the posterior median, something like that, which are optimal under more reasonable loss functions like squared error loss or absolute error loss, respectively. And those means and medians are not going to be exactly 0. But those are a richer answer because the mean and the median at least reflects the whole posterior distribution. I mean, you could talk about any characteristic of the posterior distribution, but if you choose to talk about the mode, then there's no reason why anybody should listen to you. There's some other oddities about this. Why assume sigma is known? Bayesians typically wouldn't do that. Why is there no prior information about the intercept? You could have that if you want. Why not put some prior on S, which is what the lasso engineers call the shrinkage parameter. They're going to choose that by trying this over and over again, see what value of S results in the best predictions in the testing set. But you could just put a prior on it and then estimate its posterior distribution along with everything else. It's not as if the value of S that the lasso engineer lands on is the truth or anything like that. It's just the value that predicts best out of sample. You should have, in a particular testing sample, you do have uncertainty about that, and that should be reflected in your posterior distribution. Moreover, we might ask the question, well, why should we shrink the values of beta towards 0 marginally as if they are independent of each other, which they're not? Why not we, maybe do something to shrink the beta toward the origin jointly as a whole? And we'll try to get to something like that before the end of class today. But are there any questions, particularly those of you who've unfortunately had to learn lasso previously, that they're basically making the same assumptions as the assumptions on this slide. The assumptions on this slide are a little bit weird. And the reason why there's assumptions that are a little bit weird when you go into lasso is it makes it very easy to find the posterior mode. Like the algorithm that solves the lasso problem is very efficient. It's very fast. It works very well, even if you have a large amount of data. But you have to make kind of weird assumptions for that to hold. But moreover, what lasso is seeking is an optimal point, just one set of numbers. There's not going to be anything that reflects your uncertainty about that. And that's because all they've done is find the posterior mode. In order to describe your uncertainty, your beliefs about the coefficients, you need the whole posterior distribution, not just one point. But one point is all lasso gives you. It's a point that more often than not is going to have some of those coefficients as 0, but it's not as if it's correct for you to say, I'm sure after seeing the data that this coefficient is exactly 0. That's nonsense. For any finite amount of data, you're never going to achieve that level of certainty. All you've done is just put on blinders to the rest of the posterior distribution when you focus entirely on the mode of this thing. And with the Bayesian, particularly with Stan, it's just as easy to get the whole posterior distribution under these same assumptions, and then you can describe any function that you want with the full amount of uncertainty that's remaining after conditioning on the data that you have. So in a lot of ways, the sort of philosophy of supervised learning that comes from the data mining literature is pretty consistent with the Bayesian approach to probability. Supervised learning has what they call penalty functions, but why would you penalize some coefficient from being far from 0 unless you believed before even seeing the data that the coefficient was close to 0? Like, why are you penalizing something that's not bad? Under your beliefs, you initially think it's close to 0, so you might penalize it if the data alone sort of suggests it's far from 0. But so, this idea of penalization functions maps on usually pretty exactly to a prior distribution on those, coefficients or whatever the parameters are. So the underpinnings of a lot of data mining stuff is much closer to the Bayesian view than the frequentist view. The frequentist view has nothing really in common at all with data mining approaches, but there's a bit, within data mining, there's sort of a small cohort of people that worries about probability, and probably the vast majority of them just don't worry about probability at all. They get these point estimates, and there's nothing really coherent or rational you can do with those point estimates alone, because you don't know what the uncertainty around them is. Even though it's seriously not hard these days to use Stan to get the whole posterior distribution, and then you can do like rational stuff with it. Most of the data mining thing is allergic to MCMC. They want to do optimization and optimization alone to find a single point.
If you compare like speed of like the packages that do linear optimization to like what MCMC does?
Oh yeah, the ones that do lasso are many, many, many times faster. But like this in Stan would be like a second, and this in lasso would be like a millisecond. So to say, Stan is 1,000 times slower, okay, but it's not as if we're really measuring cost on a second basis, unless you're doing like high frequency trading or something like that. For social science purposes, you can pretty much ignore computational time. It's not that important. You have to be seriously impatient for that to even matter. Computers are fast enough these days. So here's the aforementioned plot that I was talking about. So the black line here is the Laplace prior. I have it centered on 0. It has this triangular shape in log units. I simulated some data, and the red curve here is the likelihood function. The maximum likelihood estimate is actually over here close toward 2. But if we combine the prior and the likelihood, we get this posterior distribution in blue here that has this kink in it at 0 that reflects some contribution of the prior and like the likelihood of a little bit of data. So from the lasso engineer's perspective, the point estimate of beta is exactly 0. That is where the posterior mode is. But the blue line here is the whole posterior distribution. Like once we renormalize it to integrate to 1, this is in the log scale, so, you know, but we could put it in the probability scale, divide by whatever it integrates to. Now it integrates to 1, and we have a posterior distribution. And we can see this posterior distribution is asymmetric. Yes, there's a mode at 0, but it falls off faster in the negative direction than in the positive direction. So the posterior mean is going to be positive. The posterior median is going to be positive. But the lasso engineer doesn't know that because they don't get the whole posterior distribution. They just get the posterior mode and stop. So the area under the blue curve here, or the variance in the blue curve here, reflects the posterior uncertainty we have about beta conditional on these data. So yes, the most likely value for beta is 0. However, there's a lot of other values of beta that are entirely plausible. And any sort of rational decision approach needs to reflect those possibilities with the appropriate posterior probability. And you need to get draws from the posterior distribution in order to do that. So it's really the case that lasso people are just stopping with too limited an answer, when it wouldn't be difficult for them at all to get like a whole posterior distribution here without changing their assumptions. But while we're examining the assumptions, you might want to assume something more realistic than what's being assumed here, because the posterior distribution is just going to be as easy to do, maybe even easier, if you make some like more realistic assumptions, have some prior information about the intercept, something like that. Questions? Okay. So there's a package on CRAN called rStanArm, which you should install if you haven't already. When you first call library rStanArm, I didn't show it here, but there'll be some messages that one say you should specify your priors explicitly because the defaults for those may change in the future. It also suggests, as long as you're not constrained by RAM, that you use all the available cores on your machine in order to do the Markov chains in parallel. And that is easily done by specifying options, mc.cores equal some number. If you don't know how many cores your computer has, there's a function called detect cores in the parallel package that will query that for you. So whatever that number is, that'll be the number of cores that up to that number can be used by your computer when doing MCMC stuff. And the rStanArm package has a function called stan_glm. And this function, at least in terms of its syntax, is intended to be a superset of the syntax for the glm function, which you're probably already familiar with if you've been using R for a little while. Moreover, the likelihood being used when we use stan to draw from this posterior distribution is the same as the likelihood being used by the glm function when it does frequentist maximum likelihood estimates. So basically, if you know GLM, all you have to do is stick a stan underscore in front of it. You'll be able to get Bayesian posterior distribution rather than frequentist estimates. And about the only additional information that you have to provide above and beyond what you would have to provide to the GLM function is, of course, the priors, because this is going to be a Bayesian analysis. So here I'm modeling the black market premium. I'm going to use all the variables except the country name. I'm going to specify a data frame called PE risk where those variables live. The family argument, which is pretty much synonymous with the likelihood function, I want to use a Gaussian, or that's what I said I wanted to use on the previous slide. So just these two lines here would be what you would call, what you would specify if you just called GLM. If you're calling stan GLM, then you also want to specify your priors. And there's a prior family in the rstan-arm package called lasso, which does this, except S is not fixed and sigma is not fixed either. It's going to put priors on those, and we get the posterior distribution of everything. And I'm going to say I want an improper prior on the intercept. It can be any real number. And it didn't show it here. I should have, but I'm just using the default prior on the error standard deviations, which I believe is a half Cauchy in rstan-arm. That usually doesn't make too much of a difference as long as your outcome is not in ridiculous units. So the whole point of the rstan-arm package is to take popular R functions that produce frequentist estimates. You can use the same syntax, add information about the priors among the supported priors for that function, stick a stan underscore, and pretty quickly you're going to get draws from the posterior distribution. And you can do all sorts of Bayesian stuff rather than limiting yourself to frequentist stuff. So the syntax is going to be the same. The likelihood's going to be the same. The only thing that's different, you need to describe your prior beliefs in terms of additional arguments, and you're going to get back draws from the Bayesian posterior distribution rather than point estimates. Questions about that? Yes?
Your coefficients are going to be a distribution, right?
Yes, we'll show that next.
Yeah.
So if you do that and you just print out the thing called post, which is what I typically use for to convey that this is a posterior distribution, you get something like this as your summary. So it tells you what the call was, and it initially it produces point estimates. However, Stan drew and it stored from the whole posterior distribution. This is just telling you for that posterior distribution, these margins, here are the posterior medians. And that's in the first column here. So the median of the posterior distribution of the intercept is -0.3. It by default just rounds to 1 digit. You can ask for more digits if you want. The GDP variable, its median posterior distribution for that coefficient is -0.2. The median of the posterior distribution for sigma is 1.9, etc. We also have an estimator of the posterior standard deviation for each of these. This is called MAD-SD. It's technically the median absolute deviation from the median. So we calculate the medians. Then for the whole posterior draws, we calculate the absolute value of the deviation from the medians. And then we take the median of that, and then we multiply it by like 1.4, which is a consistency factor that works in the case of a normal distribution. And we have an estimator of the posterior standard deviation. So why do we do all that? Why don't we just do like SD? These median and MAD-SD are a little bit more robust. So first of all, for some posterior distributions, the mean and the variance might not exist. They might not be well defined. whereas the median always is well defined. Also, if something goes a little bit wrong, the mean and the variance and stuff like that can be overly sensitive to outliers. So the median and the MAD-SD are a little bit more robust estimators, when you're only doing a finite number of draws. But all the draws are there, and we'll show on the next slide how you can get at them. These are merely the medians and the median absolute deviations of those draws from the posterior distribution. So you don't want to just stop at this pretty brief printout summary of your posterior distribution that looks like similar to frequentist, except frequentist is not going to have median here. It's just going to be point, optimal point. This actually is the median of like 4,000 points. Okay. Question in the back. Yes.
How do you interpret
Okay, so the way you interpret it, let's say the GDP. I believe, after seeing these data, that the coefficient on like the log of per capita GDP, or however that variable was defined, I believe there's a 50% chance it's less than negative 0.2 and a 50% chance that it's greater than negative 0.2. I can tell you more if you let me describe other parts of the posterior distribution, but that is a true statement of what somebody with these priors should believe about that coefficient after seeing the data. 50% chance it's less than negative 0.2, 50% chance it's greater than negative 0.2. Now you're right that seems like kind of an incomplete description. And so you might ask, well, can you say more? And I can't. So as I was alluding to, if you just want the draws, all you have to do is as matrix. And it tells you, okay, you have 4,000 draws from the posterior distribution, 1,000 draws after the warm-up period for each of 4 Markov chains. And there are 14 dimensions to this posterior distribution, like intercept, chords, all these p variables, GDP and sigma. Those are 14 unknowns. And so in each of the columns of this thing, you have 4,000 draws from the posterior distribution that you can use to describe your posterior distribution, however you want, that's appropriate. So one way that you might do that is to call the posterior interval function, which is basically going to tell you quantiles of your posterior distribution. Here I'm asking for the interior 0.5 interval. So what we have here is an interval, let's say for GDP, where I can accurately describe my beliefs as saying there's a 50% chance that it's greater than negative 3.82 and a 50% chance that it's smaller than negative 0.03. So this is what frequentists misinterpret confidence intervals as. But this is like a genuine expression of my beliefs, or somebody who had these priors after seeing the data. They should believe there's a 50% chance that the true coefficient on GDP2 falls within this interval with probability 0.5. So conversely, there's a 0.25 probability that it's less than negative 3.82, and there's a 0.25 probability that it's greater than negative 0.03. All true statements, but these are actually statements about what I believe, intervals that I believe the true parameter falls in with a specified probability. Now I could do 90% intervals, could do 95% intervals. The endpoints of those 95% intervals are not estimated too precisely, because they're just talking like maybe 50 draws on each side or something from the posterior distribution with which to estimate those. So Bayesians will usually do sort of smaller intervals. 0.5 is pretty easy because it divides into like 0.25 and then 0.5 in the middle and then 0.25 to the right. And you can do that for any of the quantities that are being returned. I've used this regex parse to discard all the ones that start with P, in part because I don't remember what they mean, in part because they wouldn't fit on the page. But you could get the posterior intervals for those as well. So we've got the medians, and now we have, basically the endpoints of the interquartile range for my posterior distribution. So that's more description I can make about what I believe, having seen these data. Rosalie, with the question?
Yeah, and in theory, the more data you had and the more time you went through prior posterior, these things would get narrower.
Yeah.
Which is like the confidence interval.
Confidence intervals also get narrower, but they never should be interpreted as these. So confidence interval is this function that you think, okay, if I did this over and over and over again, the expectation of whether the truth parameter falls in this function is going to be 0.95. But when people obtain confidence intervals, they're almost always making statements that are inconsistent with what a confidence interval means, trying to make a statement of what they believe about the parameter or what they believe about the hypothesis, when in the frequentist way of doing things, those are not random variables. And so you can't make probabilistic statements like the null hypothesis is true with probability 0.7. The null hypothesis is either true or it's false. You don't know which, but it's not like probably true. You could say, I believe it's probably true. I believe there's a 70% chance that it's true. I believe there's a 75% chance that this coefficient on GDP2 is negative. But if you're talking about beliefs, then you already have to be Bayesian. Questions?
So we could, because we can draw any percentile.
Yeah, you can do whatever you want. Yeah.
That's basically what makes us makes this a better statement of Bayesian.
Yeah, because people want to talk about the probability of, a coefficient being negative or a hypothesis being true or whatever. It's just the frequentist dogma doesn't admit those statements. And so people have to sort of tie themselves in knots to say something that's both meaningful and supported by a frequentist estimator. It's much easier to be Bayesian provided that you have software that can, get draws to the posterior distribution, like our standard. You can also draw from the posterior predictive distribution. In this case, I'm using the same data that I did before, but that's just to show the new data syntax. And so now I get 4,000 draws, one for each draw I obtained from the posterior distribution. This thing has 62 columns, and that's because there were 62 countries in the original data set. So I'll just copy those row names over. And so this would be, what I believe about the exchange rate premium in Argentina, a distribution of 4,000 draws for what I believe the exchange rate premium would be in Argentina. I don't know what year these data were taken, but for a lot of years, that would probably be a pretty big premium. In Argentina, probably not in Australia or Austria or Belgium. I don't know about Bangladesh or Bolivia, but yeah, Argentina has been known to have more than one exchange rate. So, if I did summaries of these, I could talk about my beliefs about any of those. These are just my posterior predictive distribution of the outcome. I could do this for future data, do it for past data, whatever. Okay, so last 9 minutes, we're going to talk about a data set in the ggplot2 package called Diamonds, which has almost 54,000 observations on each of the following 10 variables that have all sorts of characteristics about diamonds that were apparently sold. X, Y, and Z are the length, width, and height of the diamond, and the rest of these things here. So think to yourself, what would be your best guess for the R squared value in a linear model of price, or if you want to, you could do log price, using, you know, these covariates or some subset of these covariates, you know, maybe with some transformations thereof or interactions, etc. You know, what would you say your best guess would be for how much of the variation in diamond price can be explained in a linear model with variables such as these? Anyone have any bling on them now? Now? Nobody? I could make a better demonstration if I had a diamond. Okay. Imagine a diamond. It's probably going to be pretty expensive. But how much of the variation in, you know, diamonds do you think could be explained by stuff like this? 0.8. I like it.
0.97.
0.97.
Are we just taking guesses on this?
Yeah, but they're not guesses. They're your best guess based on what you believe to be the case before you actually analyze these data.
We can explain a lot of them.
A lot? Okay.
Are these all the same year? Is that also?
What are the what?
This is just one cross snapshot of the year, right?
Something like that. Sure, let's say that's true. I don't know, but it's not that important. So I'm hearing kind of a lot. 0.95, 0.97. But the point is, this is your beliefs. If you think it's low, put in a low number. If you think it's high, put in a high number. Ask on Twitter.
Like I've seen like catalogs that like specify these and then have the price in front of them.
Okay.
Like that's pretty specific, right?
Yeah. So sort of if you mentally did a regression, you thought you could.
How those guys come up? They have like these sort of variables.
Yeah. So maybe the people who sell diamonds, they kind of have like a template or a formula for how they write down the prices or not. But so you can ask a friend or whatever. You just have to have something to get this process started. Here's kind of a description of what I believe now. I'm going to condition on all these data, and I'm going to get updated beliefs. How might I do that? So here is another approach to estimating a linear model that's implemented in the RStanArm package that works when you have more than 2 predictors. So again, we're going to assume the errors are normal with mean 0, standard deviation sigma. Now I'm going to separate out the intercept. Before I just called that part of X, but it makes more sense in this case to separate it out. That assumption implies that Y altogether is multivariate normal with this mean vector and variance covariance matrix equal to sigma squared times the identity matrix. I'm going to assume alpha is any real number. And then I'm going to start to get a little bit tricky. So I'm going to represent X as the product of the matrix Q and R. So in other words, I'm taking the so-called QR decomposition of X, which always exists, and produces a matrix Q such that Q transpose times Q is equal to the identity matrix, and R is an upper triangular matrix. So every rectangular or even square matrix can be written as more or less uniquely as the product of a matrix Q such that Q transpose times Q is the identity matrix, and R such that R is upper triangular. And then I'm going to define beta as R inverse times theta. Those 2 lines together imply that X times beta is equal to Q times R inverse times theta. And R times R inverse is the identity matrix. So X beta is equal to Q times theta. And I'm going to substitute Q times theta for X beta here. So what really I'm going to be doing is getting the posterior distribution of theta and then multiplying it by R inverse to get back the coefficients of beta in those same units. So what's theta? I'm going to write theta as a product of the marginal standard deviation of y, the square root of n minus 1, the square root of the r squared of the regression, and rho, where rho is any unit vector. I'm going to put a Jeffreys prior on the standard deviation of y. I'm going to set sigma, the error standard deviation, equal to the marginal standard deviation of y times the square root of 1 minus r squared. So that's sort of the leftover variation after conditioning on x. And I'm going to put a beta prior on r squared with shape parameter k over 2, which I'm not going to explain why that makes sense, and second shape parameter eta. So all you have to do, which you just did, was supply a prior mode for the r squared. I can solve for eta using the formula on Wikipedia. And now I've completely described a posterior distribution that I can draw from using r stand arm. So the only input that you have to say is what's your best guess, the mode, the prior mode for r squared, if this is the data set we're dealing with. Anyway, that is implemented by the stan_lm function. I did it on the log of price. I did the interaction between the number of carats and the log of all the 3 dimensions of the size, added dummy variables for the cut type, the color, the clarity, etc. And I put in a prior mode of 0.8 for the r squared. Get back to posterior distribution, and you might ask, well, what's the relationship between the number of carats and the price of the diamond? Not the log price, but the price in like dollars. Not at all evident from the output, but if you do the Bayesian approach, it's not at all a problem. Having estimated that, I can create a new data set using the dplyr package, where I just get like the mean value of x, the mean value of y, the mean value of z for every subset of the data that has this or that number of carats. For these categorical variables, I just take the modal value within that stratum, and I make a new data set. So that's going to have 273 rows, which is the number of unique values in the carat variable. And it has these 8 columns that I've made here. I call the posterior predict function on my new data set. That's going to give me predictions of price in log units. I merely take the anti-log of that. Now I have a description of my posterior beliefs about price for these levels of the predictors in dollars as opposed to log dollars. And I can show that relationship. So here, the gray lines reflect 90% intervals of this posterior predictive distribution. The darker points are the posterior medians, and the red points are the average of the actual prices observed in the data. So you can see there's a sharply increasing relationship, although a relationship that the model seems to capture really well, up to 2 carats. I think this is expressed relative to the weight of the diamond or something like that. In any event, for most diamonds, there's a sharply increasing relationship that the model seems to have captured pretty well. For very high carat, we have a lot more uncertainty, and the model seems to be doing less well. I think that's because once you get up to a certain number of carats, it's hard to get high quality cuts or the right color or something like that. In any event, it seems clear our model is doing less well at describing these like extremely high carat diamonds. But for most of these, model seems to be doing pretty well. And these are exactly the sorts of statements that you can make as a Bayesian that are impossible to make with like frequentist or data mining stuff, because you don't get the uncertainty and you don't have the ability to say, okay, I'm going to anti-log this, and now I'm going to talk about price in dollars. If you did your model in log dollars and you did some frequentist thing, then you're pretty much stuck with it because you don't have the ability to translate your uncertainty about stuff in log dollars to regular dollars. You have to put in the whole posterior distribution to get the posterior predictive distribution, take the anti-log of that, and now we have a posterior predictive distribution for price in terms of dollars. And this is a sort of plot that even someone who doesn't know much about Bayesian statistics or quantitative modeling in general can understand. And that's really one of the great things about the posterior predictive distribution. It's in the units of the outcome. We're not talking about theta or r squared or mu or anything like that. We're talking about diamond prices. And you know, we can put that in a plot, and we can say where our model is doing better, and we can say where our model is doing worse. We can maybe go back and try to revise our model, etc. So we'll learn more about how to do these things on Thursday and next week. In particular, on Thursday, we're going to start talking about generalized linear models, such as like Logit and Poisson and things like that. Those are also possible to do with the stan_GLM function in the rstan_arm package. So I'll see you then. Make sure to pick up the reading for Thursday if you have not done so already.